Welcome to Math 31. This is a lesson on, or a continuation of the lesson on applications of extrema, or maxima, minima. So in the previous part we looked at a few area type perimeter questions and things like that. This one I'm going to look at a few other examples, and I'm going to begin with one that is really a Math 20 pure question, but again we'll look at it a little bit differently. So it's a revenue problem. I didn't put a title for it, but that's basically what it is. We've got a ticket price for a specific event and the number of people that are known to attend at that price. And then we have a relationship between increase in price and the effect it has on attendance. So the trick is to get the ticket price that's going to maximize revenue. Now, if you're familiar with this type of application, you know that you usually get a quadratic, which we're going to. The more sophisticated economic models will not be quadratic, and they'll be more sophisticated, but the method would still be essentially the same. The Math 20 pure method is based on completing the square, so it has to be a quadratic, but the method we get now we can apply to all models like this. In any case, we want to get the ticket price that's going to maximize the revenue. Now, based on the situation, you're currently making $1,000 per event, 250 people at $4 per show. So I'm going to define the x, the variable I'm going to use at least, not to be the new ticket price, but it's going to refer to the number of price increases, or of ticket price increases. So if x is 1, it means that we have one ticket price increase of 20 cents, which means the new price is $4.20. And then we could set up a formula for the revenue, which would be equal to the product of the ticket price. So whatever the ticket price is, increase or decrease, multiplied by the number of customers. So currently, $4 times 250. And when we go further with this, we can see that no matter what the ticket price is, it'll be consistent with this formula, 4, which is what it currently is, and then plus 0.20 times x. So each increment is 20 cents, so 0.2. So if x was 1, 4 plus 0.2 would be 4.20, which is correct, and so on like that. And then the number of customers currently is 250, but it goes down by 10 for every price increase. So that's the formula. And with these ones, I always encourage you to check the domain out. And it's a pain because, like I said before, the domain often doesn't really have a big effect on anything. But it's still a good idea because when it does have an effect, it has a serious effect. And there's some debate about domain in these ones. Some people will say, well, we're restricted because we're not going to x has to be greater than 1. It has to be a natural number or something like that. I'm going to keep it pretty open-ended. I'm going to argue that the ticket price 4 plus 0.2x has to be greater than 0. In fact, we're not even going to have a ticket price of 0. Other people would say, well, 0 is mathematically okay. But I'm going to work it out like this so that you're actually not paying people to go. So take that 4 over, and then divide. Make sure you carefully divide that one out. And x is going to be greater than 4 divided by 0.2. It's negative 20. So we cannot reduce it more than 20 times. That makes sense. 20 times 0.2 is $4. And then the other thing is that the number of customers, 250 minus 10x, I also say has to be greater than 0. So you cannot have fewer than 0 customers. And some of you would say equal to 0. You could actually have 0, but I'm going to also stick to it greater than. It's a debatable point, but it makes it a little bit easier to work with. In any event, those endpoints are not going to produce a min or a max. It's not going to work that way, so I'm not going to lose a lot of sleep about it. So x is less than 25, so here's our domain. Negative 20 is less than x, which is less than 25. So it means, because it's not a closed interval, it means that I only have to check out the local extrema in order to identify what the max is, or the min. So our function would look like this. R is a function of x. If we FOIL this one out, would be 1,000 minus 40x. And then your 0.2 times 250, make sure you multiply that out carefully. So 250 times 0.2 will give you 50. So plus 50x. And then minus 2x squared. So there is our quadratic. Get the like terms together, and I'm going to organize this in descending order. So negative 2x squared plus 10x plus 1,000. And then, if you get the derivative, our prime at x, this is negative 4x plus 10. Now, when you get the critical numbers occur where the derivative is equal to 0 or where it doesn't exist. In this case, there's no point it doesn't exist within that domain, so I'm just going to set it to 0. So negative 4x plus 10 is equal to 0. So 4x is equal to 10 if you bring that 4x over. So x is equal to 10 divided by 4, which is 2.5. So we're not, had this question restricted us to natural numbers, where you had to have one increment or exactly 2 increments or whatever like that, then this number wouldn't count. But what's happening, by my reasoning, is that, okay, so instead of increasing it by 20 cents, you would just increase that 0.5 would refer to 10 cents. Debatable, but I'll stick with that. And then we want to get the ticket price that's going to maximize the revenue. I'm going to bring up a new screen. And then the ticket price that will maximize, well, the ticket price is equal to 4 plus 0.20x. So 4 plus 0.20 times that number, 2.5. So that's equal to $4.50. So a ticket price of $4.50 will maximize revenue. Now you're thinking, as am I, well, what about the test to make sure? So I will, in fact, take a look at that. I'm going to graph this as well, too. And by the way, this is a quadratic that's going to look like this in a practical sense. Its maximum is where x is equal to 2.5, so it's going to look like this with a maximum right there. So I do know it is a quadratic, but I will do the second derivative test just to be sure. And so therefore, since r prime at x is equal to negative 4x plus 10, the second derivative is equal just to negative 4. So therefore, the second derivative at x equal 2.5 is also going to be equal to negative 4. So if the second derivative is negative, this is what we get. So we know it's going to be a max. Now, that's how you tackle these ones. Now this next question is not that complicated, but there are lots of number questions in most textbooks. Here we want to get two positive numbers, so it's got to be bigger than 0, whose product is 108 and the sum of the first number plus 3 times the second is a minimum. So we are trying to minimize something. And I'm going to just look at the, it doesn't matter which variable you work with. I sort of refer to this as product, although it's also a sum. We're taking the sum of the first number plus 3 times the second number. And we're trying to minimize this p function, or whatever variable you want to call it. Now we do have two variables, so as always, well, where possible, we try to express one in terms of the other. And it's based on the idea that these have a product of 108. So x times y is equal to 108. So y is equal to 108 over x. So it means that our formula, p as a function of x, is equal to x plus 3 times 108 over x. So therefore, p at x is equal to x. If you multiply that out, you'll get 324, and then let's write that as x to the negative 1. And we should note the domain before we get too deep into this question. And once again, not a lot of restrictions in this. Both numbers have to be greater than 0. And the other thing is that x cannot be equal to 0 because of this denominator, even so. So x has to be greater than 0, but I don't see any reason why it can't be an infinitely large number. It doesn't even specify that it cannot be a decimal. So that makes our life a little bit easier. And then when we take the derivative of p at x, we'll get 1 minus 324 x to the negative 2. So p as a function of x is equal to 1 minus 324 over x squared. Now, we want to get the critical numbers, and I'm going to also cheat a little bit on this one. Because I'm not going to do interval analysis, I'm not going to bother writing this as a fraction, even though I do encourage people to do that. So I'm going to go p prime at x is equal to 0. Because with x in the denominator, the only critical number we'd get, or potential critical number where the derivative doesn't exist, would be x equals 0, and that's outside the domain. So I'm not wasting my time on that. I'll just go after this. So 1 minus 324 over x squared. And then I'm going to bring that 324 over x squared to the other side, making it positive, so that's equal to 1. And then when I multiply out the denominator, I'll get x squared is equal to 324. So x is equal to, when you take the square root, it's going to be positive 18, because x has to be greater than 0. And there we go. There's our answer, or what appears to be our answer. And then we can find y in a second, but let's do the second derivative test to ensure that this is going to be a minimum. So p prime at x is equal to 1 minus 324 x to the negative 2. When we get the second derivative, the 1 goes away, and then negative 2 times negative 324 is positive 648 x to the negative 3. So the second derivative in a more convenient form would be 648 over x cubed. So therefore, the second derivative at x is equal to 18 is equal to 648 over 18 cubed. Don't need to work that one out, because all we really need to be aware of is that the second derivative is greater than 0. So therefore, positive second derivative gives us the happy guy. So it means that it is going to be a minimum. Rarely is there any doubt, particularly when you've just got 1, but it is good to be aware of that. And then I'm going to find the y value, and then we're done. So if x is equal to 18, y, according to the formula we have, is 108 over x. So y is equal to 108 over 18, and y therefore is equal to 6. So therefore the two numbers are 18 and 6. So that's considered a pretty, almost an entry-level one, but if you haven't seen an example of it, it's easy to make a mistake on it. And then, two more questions, both kind of similar. A cylindrical can is made to hold 1 liter. So this is a type of problem you see quite a bit. It's designed to hold this much. But if you were designing this can, you would want to, presumably, minimize the amount of metal used. And of course, that's a big deal. One of the issues when pop cans or shapes are designed, one of the issues is to minimize the materials and so that you can minimize the cost of production. But this is going to be the shape that we're basically dealing with, and it has to hold 1 liter. So that's not a debatable, that's not a variable. We, in fact, are trying to minimize the amount of metal. So this is really a matter of minimizing the surface area. So our formula will be based on that. Now you've got to remember with these type of problems that surface area of a cylinder, the cylinder is made up of a top and a bottom that are both circles. So the area, I'll write this SA, is equal to 2 times the area of a circle. So that's pi r squared. And then we have a rectangle for the body of it, and the height of the rectangle would be just h. But you've got to be aware that if you did cut this thing open, the width would be the circumference of the circle because it goes all the way around. So that's 2 pi r in terms of r, not d. So it means that the other part of this is going to be 2 pi r h. That represents the surface area. And then you're thinking, well, this isn't good because I've got two variables, r and h. Now, it is sometimes possible to handle that if you have enough information, but where possible, you try to get one in terms of the other. So to me, it makes sense to convert h into r, if at all possible, based on the variables and the number of variables we have. And that's where the volume comes in, because the volume of a cylinder is pi r squared times h. So the area of the top through the height. And because this is going to be equal to 1,000 cubic centimeters, we can then isolate the h to get 1,000 over pi r squared. And then that's going to leave us with a formula. I'm just going to write this as A instead of surface area just to make it a little easier to work with. Doesn't make a lot of difference. But then this is 2 pi r, and then the h is 1,000 over pi r squared. And then if you simplify this, the r's will simplify, divide out. So you get 2 pi r squared plus, well, 2,000 pi. And then that r on the bottom I'll write as r to the negative 1 up top, because that's going to make things easier for differentiation. And before we get too carried away with it, identify the domain. And the only reasonable restriction I can think of with this is that the r has to be greater than 0. The radius, if you do not have a radius that's a positive number greater than 0, or that's redundant, a positive number period, then you don't have a cylinder. And the same thing would be true with h, that h has to be 0. It shouldn't really affect us too much. In both cases, you could have the h very, very small and then have a very broad one. you could have the r very, very small and have a very high one. But as long as they're greater than 0, we've got no problem. So when we differentiate a prime at r, this is going to be 4 pi r minus 2000 pi r to the negative 2. So in a more convenient form, that would be 4 pi r plus 4000 pi. Oops, what am I doing here? I don't want to take the second derivative. Excuse me. Getting a little ahead of myself here. A prime at r. 4 pi r minus 2000 pi over r squared. And then we look at this and try to find the critical numbers. And the situation, as we know, by the way, I did make a mistake here, didn't I? The pi is divided out. So let me get rid of that pi, lest it causes us some problems. You're probably, you're wondering out there, what's going on with that? So I want to get the critical numbers where this is equal to 0. So a prime at r is equal to 0. And once again, I'm not worried about where a prime at r doesn't exist, because r on the denominator equals 0 is not within the domain. So I go 0 is equal to 4 pi r minus 2000 over r squared. Bring the 2000 over r squared to the other side. That's equal to 4 pi r. Now when you multiply this one out, you get 4 pi r cubed is equal to 2000. So isolating the r cubed, we'll get 2000 divided by 4, which is 500. And then over top of pi. So it's not a great number, but if you take the cube root of this number, and you were asked to decimalize it over pi, to the nearest tenth, so let's see what we get. So 500 divided by pi, and then take the cubed root of that. So 5.42. Now I know I'll take that to the nearest tenth in a second, but I want to check to see whether this is a min or a max, although rarely do you overturn an answer. So I'll do the second derivative test. A prime at r is equal to 4 pi r, and then make sure you put this in its easier form to work with, so minus 2000 r to the negative 2, so that when you take the second derivative, you'll get 4 pi plus 4000, when you multiply that out, r to the negative 3. And I'm going to go right to the bottom, r cubed. So then when I take the second derivative at r is equal to 5.42, I'll get 4 pi plus 4000 over that number, 5.42 cubed. Now I don't need to work it out, because I just need to see its sign, and those are all positive numbers are being added together, so it's going to be greater than 0. So positive positive gives you this. So therefore a minimum, which is what we want. So this does represent a minimum, so we're okay. Take a few seconds to find the h value, and h is equal to 1000. Take a look at earlier in the problem, over pi r squared. So h is equal to 1000 over pi, and then 5.42 squared. So 1000 divided by pi divided by 5.42 squared. And by keeping that extra decimal there, I ensure that my answer will be accurate. You could have used your memory or your answer key. So I get 10.8 centimeters. So the dimensions should be R is equal to 5.4 centimeters and H is equal to 10.8 centimeters to the nearest tenth. Now the next question is pretty similar, and this will be it. And the difference with this one, well, first off, it's going to be exact value, but the main difference is that it has a cost issue in it. So we've got the size of the can. It's going to have to be, the volume must be that. But the materials for the base and the top are twice as expensive as the side, so it's more complicated in that respect. We still want to find the dimensions. So this one basically works as before. I'm going to right away note that R has to be greater than 0. And the same thing with H having to be greater than 0. But that won't make any difference. We're doing this one in terms of R, or I'm going to do it the same way I did the previous one at least. So the surface area is equal to 2 pi R squared, so the top and the bottom, plus the side section. And that will again be 2 pi R times H. So I won't derive all that. We know that the volume, pi R squared H, must be 500 pi. So that's equal to pi R squared H. So that's convenient, although I know when you buy most cans of any product, they usually give it the volume in, they don't usually have pi in the volume. But it will make our math easier. So 500 pi divided by pi R squared, and you'll see why, because the pi's will divide out. So H is in fact equal to 500 over R squared. So as we go into this one, the surface area, so I'm ignoring the cost issue so far. So 2 pi R squared plus 2 pi R times H is 500 over R squared. Do the mopping up. The R's will divide out. So the surface area is equal to 2 pi R squared plus 1,000. So we do have a pi here, for better or worse. And then R to the negative 1. And the cost issue, so let's deal with it now. There's a couple ways to approach it, but all I'm going to do is work with the ratio of cost. And so I'll write this as C as a function of R. The top and the bottom are twice as expensive, so I'm just going to multiply that by a factor of 2. So 2 times 2 pi R squared. And then the other one is just a factor of 1, because that's what it costs. So if you didn't put the 1 there, it's not going to make any difference. And R to the negative 1. So the cost function could be simplified then as 4 pi R squared plus 1,000 pi R to the negative 1. So when you differentiate it, C prime at R, you will get 8 pi R minus 1,000 pi R to the negative 2. So I'll bring up a new screen, but I will find the critical numbers. And the critical numbers will occur where that's equal to 0. Once again, R being equal to 0 is not going to be an issue. That's outside the domain. So it's really only the critical numbers we are concerned with that are found where it's equal to 0. So C prime at R equals 0. So 0 is equal to 8 pi r minus 1000 pi over r squared, I believe. Yes, so I got that on the bottom. I'll bring the 1000 pi r squared to the left side to make it positive, and that's equal to 8 pi r. Reminder again that I would normally get a common denominator, set it to 0, and work with it like that. But the reason I would do that is because it would make my interval analysis easier. And because I'm not doing that for the application, it's just easier this way. So cross and multiply, and you get 8 pi r cubed is equal to 1000 pi. So r cubed, when you divide it out, the pi's will go away, and then when you get 1000 divided by 8, and we get a break, that's equal to 125. So r is equal to the cube root of 125, so it's 5. So now, let's quickly do the second derivative test, and as always, we're not expecting anything to change. So c prime at r is equal to 8 pi r minus 1000 pi r to the negative 2. So the second derivative, c double prime at r, is equal to 8 pi plus 2000 pi, and then r to the negative 3, so I'll write that on the bottom. So you can see where this one is going. C double prime at 5 is equal to 8 pi, so that's positive, plus another positive number. So I'm satisfied. The second derivative is greater than 0, so it's positive, positive. That's going to be a minimum. So we find h, and then we're out of here. And h would be found by using the original volume formula, 500 divided by, I believe, r squared. So h is equal to 500 over 5 squared. Divide that out, and we should be in good shape. So 500 divided by 25, probably shouldn't need a calculator for that one. H is 20. So therefore, the dimensions should be r is equal to 5 centimeters and h equal to 20 centimeters. So that should take care of these problems. The next batch will be, a variety of volume type things in economic setups where you're trying to minimize or maximize. Thank you for your time.